All right, everybody. I wanted to do a short video today explaining what the activity is for today and how it kind of builds on the activity from the last lesson. So last time we took a look at the solar system and we looked at some of these illustrations showing the different planets and how none of them are really quite right. In most of them, the planets aren't accurately sized. They often show Earth being too big and the sun being just way too small. And the reason for that is largely uh, practical. In order to show artwork of the solar system, well, you need to realistically fit all of the planets in one image. In the last lesson, you drew the planets to scale size to show what they were really like. In this lesson today, what I want you to do is to draw a diagram that shows their distance apart from each other to scale. How close are they really? And when we look at these images, well, it gives this kind of misleading impression that the planets are actually pretty close together and equally spaced. Well, it turns out that's not true. Here's one from National Geographic, and it looks like every planet is equally spaced in the universe or in the solar system, and that's just not the case. Something that is kind of interesting, though, is that for the most part, the planets are all in the same plane. There's a little bit of variation, but very little. So they are all lined up with each other, but the distances between them are nothing like these diagrams show. And that's what I want you to work on today, is to do a drawing that shows the scale distances between the planets. So what you'll find is a worksheet that looks like this. And you're going to use your reference table to find the mean distance from the sun for each planet. So in the last lesson, we used page 15 of the reference table. And again, I'll put a link to this if you need it. You can work from the PDF if you don't have your reference table at home. But on page 15 in the reference table, we have our solar system data. And here we can see mean distance from the sun. We looked at period of revolution and rotation in the last lesson. And remember, Venus has that longer day than a year, which is just very odd. It actually takes more time to go through one day on Venus, and that day is long, 243 Earth days for one Venus day. And it would take over a year on that planet to do it, longer than one trip around the sun. And we looked at some of these other interesting observations. Something I forgot to mention in the last video was if we look at the revolution and rotation rate for the moon, they're equal. 27.3 days for the moon to go around not the sun, but the Earth one time. And it also takes 27.3 days for the moon to rotate once. Now, that's kind of an interesting thing. The rate of revolution around Earth and the rate of rotation on the moon's axis are equal to each other. And that's not a coincidence. That means something. And if you really think about what that means for a minute, what it means is that we always ever see one side of the moon. One side of the moon is always facing us because as the moon revolves in its orbit around Earth, it's rotating at the same rate. So as it moves around Earth, it turns a little bit as it goes around Earth. And it does this in such a way that we never see its backside. If we were in the classroom, a simple activity that I usually do is I have some student in the center of the classroom hold a globe. And then I pretend that I'm the moon. And I move in this way where I can walk around the classroom. And if you imagine somebody in the center of the classroom holding a globe, pretending they're Earth, I can certainly walk around that person and never show my back to them. I can always have my front facing them. And that's essentially what the moon does. If this idea of rotation and revolution is a little confusing, you can think of it as gravitational lock, which it is. And if you imagine a dancer, for example, swinging their partner around in circles, they're always going to be facing each other. If they're hand in hand and one person is spinning the other person through the air, they're always going to be facing each other. For that reason, we always see one side of the moon, and we call that the near side of the moon. The side we don't see, we call the far side. Some people refer to it as the dark side. I don't like that term because sometimes that far side of the moon is completely illuminated with sunlight and is not dark at all. But that's really getting into another lesson in itself. Anyway, we also talked about in the last lesson, Saturn has a density of 0.7 less than water. If we could somehow take Saturn and drop it in a big pool of water, it would actually float, which is very interesting. We could see the period of rotation. Some planets rotate very quickly, like Jupiter. A day on Jupiter is under 10 hours. But there's really no discernible pattern in the length of a day. But if we look at the period of revolution, there certainly is a pattern. And the further we get from the sun, the more time it takes for a year. Now, anyway, what I want you to do is use these distances from the sun, which are listed here, and you're going to put them into this data table here. So mean distance from the sun in kilometers, you just get from the reference table. Notice that's in millions of kilometers. So that's just something to think about. Space is really big. We're dealing with 57.9 million kilometers, not 57.9. Okay, so anyway, you're going to put in your distances here. And then remember, this is millions of kilometers. You're going to convert that to a scale distance that we could work with on a piece of paper. And here I figured out a scale that should work for most of you. If you do 1 centimeter is equal to 100 million kilometers, that should work out fairly nicely, I think. So take your mean distances from the sun, but remember you have to put them down as millions of kilometers. So don't just put down 57.9, you have to convert it into millions. And then use this scale, 1 centimeter equals 100 million kilometers. Basically, whatever you get for your distance here, you're going to divide by 100 million. And that's going to give you a scale distance in centimeters that you can then work with. To create your drawing, basically what you're going to do is draw these planets on a piece of paper, these distances apart. Now, I'm not concerned that you draw the size of the planet to scale. You did that the other day. So you can kind of just freehand sketch the planet. That doesn't have to be to scale. But I want you to draw the distances between the planets to scale. Now, to do this, if we look at Neptune, when we work it out, is quite far from the sun. And maybe we'll do Neptune together. 498.3. But we have to convert that into millions of kilometers. So we can't just leave that as is. You know, and I worked all this out on a piece of paper. Let me get it here. Okay, sorry about that. Okay, so for Neptune, if we convert it into millions of kilometers, I get 496. 1, 2, 3. Okay, and that would be equal to the distance of Neptune in millions of kilometers, or at least it should be. I'm actually working from a different version of the reference table. Let's make sure that still matches. They have 8.3. 4496. Yeah, so we'll match it to the reference table. So I'm going to change this to an 8. Whoops, 8. And then put a 3 here. So it's the same as what you have. Okay, so anyway, that's the distance to Neptune converted into millions of kilometers. Okay, because remember, this is in millions. So you have to add zeros, right? And then to get the scale distance, I'm going to divide by 100 million. So when I divide this by 100 million, I should get 44.0 0.983 centimeter, which means basically 45 centimeters. Which means basically on a piece of paper, you're going to draw a line 44.983 or basically 45 centimeters long, and mark Neptune on one end and the sun on the other. Remember, all of these distances are from the sun, not from one planet to the next. This is going to be a lot like the geologic timeline activity that you did, but now it's not time, it's distance. So on one end of your line, you're going to have the sun, and on the opposite end of the line, you're going to have Neptune at 44.983 centimeters. To get that distance of 45 centimeters roughly, you'll probably need to take two pieces of paper and attach them together end to end the long way, like you did when you made the geologic timeline. So it's going to be kind of similar to that. And then you're going to work out the rest of these distances. Remember, they're all measured from the sun. It's not the distance from planet to planet, it's the distance from the sun every time. So each time that you figure out where a planet goes, you're going to measure from the sun out on your line. All of the planets are basically in the same plane, so we could draw a line to represent the plane of the solar system, and you can put the planets on that line. And again, the size of the planets does not need to be to scale. You can kind of freehand that. But just remember that our first four planets, Mercury, Venus, Earth, and Mars, are what are called terrestrial planets, meaning they have dirt. They're rocky. They have a soil and a ground. And they tend to be smaller planets. And then when we get into Jupiter, Saturn, Uranus, and Neptune, these are what are called Jovian planets or gas giants. And these planets are much, much larger. So, draw your circles roughly accordingly. So, make these first four kind of smaller, make these last four kind of bigger. But what I'm really looking for is the distances to scale on the paper. So, do the drawings and then insert or attach a photograph of your drawing. And there's just a couple questions that I'm going to add to this, but they're going to be pretty simple. And that should be it. So anyway, if you get stuck with anything, let me know. On the last activity, some of you were asking for some help with the math or measuring the diameter of the sun and so on. If you get stuck in any of the math or anything like that, just let me know and I could probably help you work it out. Okay, so good luck with that, and let me know if you have any trouble.